Hello, and welcome to Sleep Archive. We live at the bottom of a vast, invisible ocean. We rarely feel its weight, but it presses against us with the force of nearly 15 pounds on every square inch of our skin. It is a restless, turbulent fluid that governs every aspect of our survival, from the food we grow to the cities we build. We call it the weather. To the casual observer, the sky is a chaotic theatre of random events. One day it is a still blue void. The next, it is a churning engine of electricity and ice. But there is nothing random about the weather. It is a grand thermodynamic play, a constant struggle for balance across a spinning planet. It is the story of energy moving from where it is plentiful to where it is scarce. In this series, we will look past the clouds to the physics driving the storm. We will see how a sunbeam hitting the equator can trigger a blizzard at the poles. We will discover how water acts as a giant battery, storing the sun's heat and releasing it with the power of a nuclear weapon. We will learn why the air turns, why the rain falls, and why, despite our most powerful supercomputers, the sky remains a master of chaos. Prepare to look up. This is the science of weather. To understand weather, we must first stop thinking of the atmosphere as empty space and start seeing it for what it truly is, a fluid. Just like the water in the sea, the air around us has mass. It flows in currents, and it exerts pressure. We are effectively deep-sea creatures, living on the floor of an aerial ocean. This ocean is held to the earth by gravity, which creates a vertical gradient of density. Because air is compressible, the weight of the entire atmosphere above us squeezes the air at the surface. At sea level, the air is thick and heavy, pressing against us with a force of nearly 15 pounds per square inch. But as you climb a mountain, there is less air above you pressing down, so the pressure drops. This difference in pressure, high versus low, is the fundamental engine that drives the wind. Air always wants to move from high pressure to low pressure, trying to equalize the imbalance. The atmosphere is organized into distinct layers, but for weather, we only truly care about the bottommost slice, the troposphere. Extending roughly 7 to 10 miles up, this layer contains 80% of the atmosphere's total mass and 99% of its water vapor. It is the only place where weather happens. The defining characteristic of the troposphere is a strange rule of physics. As you go higher, it gets colder. On average, the temperature drops about 3.6 degrees Fahrenheit for every 1,000 feet you climb. This happens because of a process called adiabatic cooling. Think of a parcel of air near the ground. As it is heated by the sun-warmed earth, it expands and becomes less dense, causing it to rise like a hot air balloon. As it rises into the thinner air of the upper atmosphere, there is less pressure to hold it together. The parcel expands outward. To expand, the molecules have to push against the surrounding air, which requires energy. Since that energy comes from the heat of the air itself, the parcel cools down. This cooling by expansion is the primary reason clouds form. As the air cools, it loses its ability to hold water vapor as a gas. Eventually, the invisible gas condenses into visible liquid droplets. If the air didn't get colder as it rose, our planet would have no clouds, no rain, and no life. The boundary at the top of this layer is called the tropopause. It acts as a lid on our weather. Here, the temperature stops falling and begins to rise again in the stratosphere above due to the ozone layer absorbing UV light. This temperature inversion creates a physical barrier that prevents most clouds from rising any further. When you see a massive thunderstorm with a flat anvil top, you are looking at a cloud that has literally hit the ceiling of the world. It can go no higher, so it is forced to spread out sideways. The atmosphere is a machine, and like any machine, it requires fuel to run. That fuel is heat. The source of this heat is 93 million miles away, the sun. Every second, the sun blasts Earth with 174 petawatts of energy. To put that number in perspective, it is roughly 10,000 times the total energy consumption of every human on the planet combined. But this energy does not hit the Earth evenly. This uneven heating is the fundamental imbalance that drives all weather. Because the Earth is a sphere, the sun's rays strike the equator directly, concentrating heat in a small area. At the poles, the same amount of sunlight hits at a shallow angle, spreading the energy over a much larger surface area. This creates a massive temperature gradient. The equator is constantly gaining heat, and the poles are constantly losing it. The atmosphere's primary job is to fix this imbalance. It is a giant heat engine designed to move excess energy from the tropics to the poles. If the atmosphere stopped moving, the equator would become uninhabitable hot, and the poles would freeze solid. The first step in this engine is albedo. Not all sunlight is absorbed. Albedo is a measure of reflectivity. Dark surfaces, like forests and oceans, have low albedo. They absorb sunlight and warm up. Light surfaces, like ice caps and clouds, have high albedo. They reflect sunlight back into space like a mirror. This creates a feedback loop. The snowy poles reflect most of the sun's heat, keeping them cold. The dark oceans absorb heat, keeping them warm. But as the planet warms, the ice melts, exposing dark ocean water underneath. This lower albedo absorbs more heat, melting more ice. A dangerous cycle known as the ice albedo feedback. Once the ground absorbs sunlight, it re-radiates that energy as infrared heat. This warms the air directly above it. Warm air is less dense than cold air. Its molecules are vibrating faster and pushing each other further apart. Because it is lighter, it floats upward. This vertical movement is called convection. It is the same process you see in a pot of boiling water. Hot fluid rises, cools at the surface, and sinks back down. In the atmosphere, massive columns of warm air rise from the surface, carrying heat energy up into the sky. As they rise, they create a vacuum at the surface, a low pressure zone. Surrounding air rushes in to fill this gap. We feel this horizontal movement of air as wind. So, when you feel a breeze on your face, you are actually feeling the earth trying to equalize its temperature. You are feeling the atmosphere's desperate attempt to shuffle heat from a warm place to a cold place. The wind is simply the byproduct of the planet's uneven heating. However, this simple convection loop, air rising at the equator and sinking at the poles, is complicated by one crucial fact. The Earth is spinning. If the Earth did not rotate, the weather would be simple. A single massive loop of air would rise at the equator, flow north to the poles, cool down, sink, and flow back to the equator. It would be a boring, predictable cycle. But the Earth spins, and it spins fast. At the equator, the surface is moving at over 1,000 miles per hour. This rotation breaks the simple loop into 3 distinct cells and creates the complex wind patterns we see on the news every night. The force that causes this is called the Coriolis effect. Imagine you are standing on a merry-go-round that is spinning counterclockwise. If you try to throw a ball straight across to a friend on the other side, the ball will appear to curve to the right. The ball actually traveled in a straight line, but because you and your friend moved while the ball was in the air, the path looks curved relative to the spinning surface. The same thing happens to the wind. Because the Earth spins from west to east, any air moving towards the poles gets deflected. In the northern hemisphere, air is always deflected to the right. In the southern hemisphere, it is deflected to the left. This deflection prevents the warm air from the equator from making it all the way to the North Pole. Instead, it gets twisted. This creates a 3-cell engine that wraps around the entire planet. The first gear in this engine is the Hadley cell. This is the largest and strongest circulation pattern. It starts at the equator, where the sun is strongest. Hot, moist air rises rapidly, creating a band of low pressure and constant thunderstorms known as the Intertropical Convergence Zone, ITCZ. This is the rain belt of the world. As this air rises and spreads out towards the poles, it cools. By the time it reaches roughly 30 degrees latitude, about the location of Texas or northern Africa, it has become cold and dense. It sinks back down to the surface. This sinking air is the key to understanding the world's geography. Sinking air suppresses clouds and rain. It creates a zone of permanent high pressure. This is why almost all of the world's great deserts, the Sahara, the Arabian, the Kalahari, the Australian outback, are located around 30 degrees latitude. They are the exhaust pipes of the Hadley cell, where dry air is constantly pushing down, preventing life-giving rain from forming. From this desert belt, the air flows back towards the equator along the surface. But because of the Coriolis effect, it doesn't flow straight south. It gets bent to the west. These are the trade winds. For centuries, sailors relied on these steady, easterly winds to push their merchant ships across the oceans. They are the most consistent winds on Earth. The second gear is the ferrule cell. This sits between 30 and 60 degrees latitude, the zone where most of the United States and Europe lie. This cell is unique because it moves in the opposite direction to the others. It acts like a ball bearing between the tropical Hadley cell and the freezing polar cell. In this zone, the surface winds flow from the southwest to the northeast. These are the westerlies. This is why weather in the US almost always moves from west to east. If a storm hits California today, it will likely hit New York in 3 days. The ferrule cell is a turbulent mixing zone, a battleground where warm tropical air constantly clashes with cold polar air, creating the dynamic, changing seasons we experience. The final gear is the polar cell. This is the weakest of the three. Cold, dense air sits over the poles, creating a permanent high-pressure cap, the polar high. This frigid air sinks and flows southward along the ground. As it moves, the Coriolis effect bends it to the west, creating the polar easterlies. Where the cold polar easterlies crash into the warmer westerlies, around 60 degrees latitude, the warm air is forced up over the cold air. This creates the polar front, a permanent storm track that circles the top of the world. This is the birthplace of the massive low-pressure systems that batter places like Seattle, the UK, and Scandinavia. So, the global wind system is not chaos. It is a precise 3-gear machine powered by the sun and steered by the spin of the Earth. It is a planetary air conditioning system, constantly struggling to balance the books of thermal energy. If the atmosphere is a heat engine, water is the battery. It is the storage medium for the sun's energy. Water is a strange molecule. It is the only substance in the known universe that exists naturally in all three states of matter: solid, liquid, and gas, within the narrow temperature range of our planet. This versatility allows it to move energy around the globe with incredible efficiency. The key to this process is latent heat. Most people think of heat as something you can feel, sensible heat. If you touch a hot stove, you feel the energy transferring to your hand. But there is a hidden form of energy locked inside the molecular bonds of water. When sunlight hits the ocean, it warms the water molecules. As they absorb energy, they vibrate faster. Eventually, they break free from the liquid surface and become a gas, water vapor. This process is evaporation. Evaporation is a cooling process. It requires energy to break those liquid bonds. That energy is taken from the surrounding environment. This is why sweating cools your body. As the sweat evaporates, it steals heat from your skin to fuel the phase change. Crucially, that heat energy doesn't disappear. It is stored inside the water vapor molecule. It becomes latent or hidden. A single gram of water vapor holds about 540 calories of latent heat energy. This is a massive amount of power. The atmosphere is filled with invisible, floating batteries, each charged with the heat of the tropical sun. This vapor is carried by the winds, sometimes traveling thousands of miles from where it evaporated. Eventually, it encounters cooler air, usually by rising. As it cools, the molecules slow down. They can no longer fight the attractive forces between them. They snap back together into liquid droplets. This is condensation. Condensation is a warming process. It is the exact opposite of evaporation. When the water turns back into a liquid, it releases that stored latent heat into the surrounding air. This release of heat is the engine of a storm. When you see a towering cumulonimbus cloud exploding upward, you are watching a massive release of latent heat. The condensing water is literally heating the air inside the cloud, making it more buoyant, causing it to rise faster, which sucks in more moist air from below, which condenses and releases more heat. It is a runaway feedback loop. A large thunderstorm releases more energy in 20 minutes than a small nuclear weapon. This cycle, evaporation storing heat, transport by wind, and condensation releasing heat, is how the Earth moves energy from the hot equator to the cold poles. Without water vapor acting as a battery, the poles would be far colder, the tropics far hotter, and our weather would be essentially lifeless. To understand how much water is in the air, meteorologists use two numbers: relative humidity and dew point. Relative humidity is the number most people know, but it is deceptive. It tells you how close the air is to being full of water vapor, expressed as a percentage. But the capacity of the air changes with temperature. Warm air is like a large sponge. It can hold a lot of water. Cold air is like a tiny sponge. It can hold very little. So, 50% humidity on a hot day represents a huge amount of water. 50% humidity on a cold day represents almost nothing. The dew point is a much more honest number. It is an absolute measure of the moisture in the air. It is the precise temperature at which the air would need to be cooled for it to become 100% saturated. If the air temperature cools down to the dew point, the sponge is full. The air cannot hold the water as a gas anymore. It must dump the excess. This is when dew forms on the grass, fog forms in the valley, or clouds form in the sky. If the dew point is 60 degrees, the air feels comfortable. If it is 70 degrees, it feels tropical and oppressive because the air is so saturated that your sweat cannot evaporate. The battery of the atmosphere is fully charged, waiting for a spark to release its energy. If water vapor is the battery of the weather, clouds are the exhaust fumes of that energy release. They are the visible manifestation of the atmosphere's cooling engine. But a cloud is not just water vapor. In fact, water vapor is invisible. If you see a cloud, you are looking at liquid water or solid ice suspended in the air. The birth of a cloud requires 3 ingredients: water vapor, cooling, and a surface. This third ingredient is often overlooked. In a perfectly clean lab environment, you could cool air down to 300% relative humidity, and a cloud would still not form. The water molecules need something to grab onto to transition from gas to liquid. In the atmosphere, this something is cloud condensation nuclei, CCN. These are microscopic particles floating in the air: dust, smoke, sea salt, pollen, and even bacteria. Every single droplet in a cloud has a tiny speck of dirt at its center. Without this dust, the water molecules would simply bounce off each other. The dust provides a surface for the water to cling to, overcoming the curvature effect that normally tears tiny droplets apart. When a parcel of air rises and cools to its dew point, the water vapor condenses onto these nuclei. This creates billions of microscopic droplets. These droplets are incredibly small, roughly 10 to 20 micrometers in diameter. They are so light that the slightest updraft of air keeps them suspended, defying gravity. This is why clouds float. They are not weightless. A typical cumulus cloud weighs about 1 million pounds, but that weight is spread out over such a massive volume that the air resistance dominates gravity. Clouds come in infinite shapes, but they fall into 2 primary physical categories based on how the air is moving: cumuliform and stratiform. Cumuliform clouds, like cumulus, are the puffy clouds. They are born from convection, instability. This happens when a specific bubble of air is warmer than its surroundings. It rises rapidly, like a hot air balloon. As it shoots up, it cools and condenses, creating a cloud with a flat base, the exact altitude where the temperature hits the dew point, and a towering cauliflower-like top. These clouds represent vertical energy. They are localized, turbulent, and often short-lived. Stratiform clouds, like stratus, are the flat clouds. They look like a grey blanket covering the sky. These are born from advection stability. This happens when an entire layer of air is forced upwards slowly, usually by a warm front sliding over a cold air mass. The air doesn't shoot up in bubbles. It lifts like a massive sheet. The cooling happens evenly across a huge area, creating a uniform layer of cloud that can stretch for hundreds of miles. There is a third, strange state of water that exists only in the clouds: supercooled water. We are taught that water freezes at 32 degrees Fahrenheit. This is true for a puddle on the ground. But in the pure, clean air of the upper troposphere, water behaves differently. Without a seed to start the crystallization process, like an ice nucleus, water can remain liquid at temperatures as low as -40 degrees Fahrenheit. This supercooled water is a loaded gun. It is liquid, but it is desperate to freeze. The moment it touches anything solid, like an airplane wing or a snowflake, it instantly snaps into ice. This phenomenon is responsible for the dangerous icing that brings down aircraft, and it is the fundamental mechanism that allows rain to form in cold clouds. Most of the time, the water in a cloud stays there. The droplets are so tiny, about 10 microns across, that air resistance overwhelms gravity. They float. For rain to fall, these microscopic droplets must grow heavy enough to overcome the updraft, keeping them suspended. They need to become raindrops, which are about 2 millimeters across. To bridge this gap in size, the droplet must increase its volume by a factor of 1 million. There are two primary ways this happens, depending on the temperature of the cloud. In the warm tropics, where the cloud temperature is entirely above freezing, the process is simple: collision, coalescence, warm rain. Imagine a cloud as a crowded room of floating balloons. Some balloons are slightly larger than others. Because they are larger, they fall slightly faster through the air. As a large droplet falls, it collides with smaller, slower droplets in its path. It absorbs them, growing bigger. Now that it is bigger, it falls even faster, sweeping up even more droplets. It is a runaway snowball effect. Eventually, the drop becomes too heavy for the updraft to hold, and it falls out of the cloud as rain. However, outside of the tropics, and in almost all significant rainstorms, the process is much more complex. It involves ice. This is the Bergeron process, cold rain. In the middle and upper latitudes, most clouds are a mix of ice crystals and supercooled liquid water droplets. This coexistence is unstable. At the same temperature, say -10 degrees Celsius, the saturation vapor pressure over ice is lower than over liquid water. This means water molecules find it easier to escape from a liquid droplet than from an ice crystal. Nature hates imbalance. The water molecules evaporate off the liquid droplets and deposit directly onto the ice crystals. The ice crystals grow rapidly at the expense of the water droplets. The liquid droplets shrink and vanish, while the ice crystals become heavy snowflakes. So, almost every raindrop that hits your head in Europe or North America started its life as snow. High up in the cloud, these snowflakes grow large and heavy. They begin to fall. As they fall through warmer air near the ground, above 32 degrees Fahrenheit, they melt. They turn into rain. If the air near the ground is below freezing, they stay as snow. But sometimes, the atmosphere creates a dangerous sandwich. Imagine a layer of warm air above freezing, sandwiched between two layers of cold air, one high up, one near the ground. 1. Sleet. The snowflake falls into the warm layer and melts into a raindrop. Then, it falls into the deep, cold layer near the ground. It has time to refreeze into a tiny pellet of ice before it hits. This is sleet. It bounces off your windshield. 2. Freezing rain. The snowflake falls into the warm layer and melts, but the cold layer near the ground is very shallow. The raindrop doesn't have time to refreeze in the air. It hits the ground as liquid water. However, because the ground itself is below freezing from previous cold weather, the water instantly freezes upon contact. It coats trees, power lines, and roads in a heavy glaze of solid ice. This is the most destructive form of winter precipitation. Finally, there is hail. Hail is not a winter phenomenon. It is a summer one. It requires the violent updrafts of a thunderstorm. A raindrop freezes and is lifted by a powerful updraft into the bitter cold upper atmosphere. It collects a layer of supercooled water, which freezes instantly, opaque ice. Then, it might fall back down into a wetter, warmer part of the cloud, collecting a layer of liquid water that freezes slowly clear ice. The hailstone is caught in a cycle, up and down, adding layer after layer like an onion. Eventually, it becomes too heavy for even the strongest updraft to support. A grapefruit-sized hailstone requires an updraft of 100 miles per hour. It plummets to Earth, a solid chunk of ice born from the heat of summer. If the atmosphere is a global war, the air masses are the armies. These are massive bodies of air, often thousands of miles across, that have conquered a specific region of the Earth. By sitting over that region for days or weeks, the air takes on the characteristics of the land or water beneath it. Meteorologists classify these armies by two simple traits: temperature and humidity. If an air mass sits over the frozen tundra of Canada, it becomes cold and dry. This is continental polar CP air. If it sits over the Gulf of Mexico, it becomes hot and wet. This is maritime tropical MT air. There are others, maritime polar, continental tropical, but these two are the primary combatants in the weather of the Northern Hemisphere. These air masses do not stay put. The global circulation, the westerlies, pushes them around the planet. Eventually, they collide. When two air masses with different temperatures meet, they do not mix. Fluid dynamics forbids it. Just as oil floats on water, warm air floats on cold air. They remain distinct, separated by a sharp boundary. This boundary is called a front. The name comes from World War I. Norwegian meteorologists, looking at their weather maps in 1918, noticed that these lines of conflict looked exactly like the battlefronts of Europe. The type of weather you get depends entirely on which army is advancing. The cold front, the bulldozer. A cold front happens when a mass of cold, dense air advances into a region of warm, lighter air. Because cold air is heavy, it hugs the ground. It acts like a wedge or a bulldozer plow. It slams into the warm air and forces it upward violently. The slope of a cold front is steeper ratio of about 1 to 50. For every 50 miles you go back, the front rises 1 mile. This steep angle forces the warm air to rise rapidly. As we know, rising air cools and condenses. Because the lift is so sudden and vertical, the clouds that form are tall and narrow, cumulonimbus. This is why cold fronts bring short, violent storms. You get a sudden drop in temperature, a shift in wind direction, and a burst of heavy rain or thunderstorms. But because the front moves fast, up to 30 miles per hour, the bad weather clears quickly. The sky turns blue, and the air becomes crisp and dry. The warm front, the ramp. A warm front is the opposite. It happens when warm air advances into a region of retreating cold air. Warm air is light. It cannot push the heavy cold air out of the way. Instead, it slides over the top of it. The slope of a warm front is very shallow, a ratio of about 1 to 200. It is like a long, gentle ramp. The warm air slowly glides up the back of the cold air mass. This gradual lift creates wide, flat layers of clouds, stratus and nimbostratus. The weather sequence of an approaching warm front is slow and ominous. First, you see high, wispy cirrus clouds, mare's tails, caused by the very tip of the warm air wedge high above you. Then, the sky turns a milky white, cirrostratus. Then, the clouds lower and thicken into a grey blanket, altostratus. Finally, the steady, dreary rain begins. Unlike a cold front, the rain from a warm front is rarely violent. It is a steady drizzle that can last for days because the front moves slowly, roughly 10 to 15 miles per hour, and creates a huge shield of clouds ahead of it. The stationary front, the standoff. Sometimes neither air mass is strong enough to move the other. The boundary stalls. The cold air flows parallel to the warm air, like traffic on a two-way street. The weather along this stationary front is miserable. Constant clouds and rain for days on end, until a wave of low pressure ripples along the front and gets things moving again. The occluded front, the merger. Finally, because cold fronts move faster than warm fronts, a cold front will eventually catch up to the warm front ahead of it. When this happens, the warm air is lifted completely off the ground. The cold air behind the storm crashes into the cool air ahead of the storm. The warm air is trapped above them, cut off from the surface. This is an occluded front. It signifies that the storm system has reached its peak intensity and is beginning to die. The temperature difference, the fuel, has been equalized. This dance of air masses creates the swirls of low pressure we see on satellite maps, mid-latitude cyclones. These are not random spirals. They are the atmosphere's way of mixing the armies, turning potential energy temperature difference into kinetic energy, wind D2, to bring the planet back into balance. A thunderstorm is the atmosphere's way of correcting a mistake. The mistake is instability. In a stable atmosphere, cold, heavy air sits near the ground, and warm, light air sits above it. This is balance. But the sun heats the ground, and the ground heats the air touching it. Eventually, you get a bubble of hot, humid air trapped beneath a layer of colder, drier air. This is top-heavy. It is like trying to hold a beach ball underwater. The moment you let go, it shoots up. That letting go is the birth of a thunderstorm. To build one, you need 3 ingredients: moisture fuel, instability, the desire to rise, and lift, the spark. The spark can be anything: a cold front acting like a plow, a sea breeze, or even a mountain slope. Once the air is nudged upward, if it is warmer than its surroundings, it becomes buoyant. It rises on its own. This is the cumulus stage. As the invisible bubble of air rises, it expands and cools. When it hits its dew point, the water vapor condenses into liquid droplets. As we learned, condensation releases latent heat. This is crucial. The heat warms the air inside the cloud, making it even lighter and more buoyant. It rises faster. This sucks in more humid air from below, which condenses and releases more heat. It is a runaway chain reaction. The cloud explodes upward, growing from a tiny puff to a towering monster, cumulonimbus, in just 15 minutes. Inside this tower, the updraft is screaming upward at speeds of up to 100 miles per hour. This wind is strong enough to hold millions of tons of water and ice suspended in the air. Eventually, the cloud hits the roof of the troposphere, the tropopause. It spreads out into the classic anvil shape. At this point, the raindrops and hailstones become too heavy for the updraft to hold. They fall. This triggers the mature stage. As the rain falls, it drags air down with it due to friction. Furthermore, some of the rain evaporates into the dry air around the cloud edges. Evaporation absorbs heat, cooling the air. This cold, heavy air crashes down towards the ground. This is the downdraft. When the downdraft hits the ground, it spreads out in all directions. You feel this as the gust front, that sudden blast of cold wind that hits you just before the rain starts. This is the storm exhaling. In a normal single-cell thunderstorm, the kind that pops up on a hot summer afternoon, this downdraft is the storm's suicide note. The cold air spreads out and cuts off the supply of warm, humid air feeding the updraft. The fuel line is severed, the updraft dies, the rain stops, and the cloud evaporates. This is the dissipating stage. The whole life cycle takes about 30 to 60 minutes, but sometimes the atmosphere adds a fourth ingredient: wind shear. Wind shear is a change in wind speed or direction with height. For example, the wind at the ground might be blowing from the south at 10 miles per hour, but at 20,000 feet, it is blowing from the west at 50 miles per hour. This shear tilts the storm. Now, when the rain and the downdraft fall, they don't fall straight down onto the updraft. They fall to the side. The updraft, the intake, and the downdraft, the exhaust, are separated. The storm doesn't choke itself. Instead, the cold downdraft acts like a mini cold front, scooping up more warm air and feeding it into the tilted updraft. The storm becomes a self-sustaining engine. It can last for hours, travel for hundreds of miles, and grow into a supercell, a rotating giant capable of producing baseball-sized hail and tornadoes. The energy involved is staggering. A typical thunderstorm holds the energy equivalent of a small atomic bomb. A large supercell holds the energy of a hydrogen bomb, and at any given moment, there are roughly 2,000 of these bombs exploding all over the Earth. If a thunderstorm is a heat engine, lightning is its spark plug. It is one of the most violent and energetic events in nature, a momentary breakdown of the atmosphere's ability to insulate electricity. To understand lightning, we must look inside the cloud at the microscopic level. A cumulonimbus cloud is a chaotic place. Updrafts are carrying billions of tiny ice crystals upward. Downdrafts are carrying heavier pellets of soft hail graupel downward. These particles collide. When they crash into each other, electrons are stripped off. This is the triboelectric effect, the same static electricity you get when you rub a balloon on your hair. Through a quirk of physics, the lighter ice crystals tend to lose electrons and become positively charged. The heavier graupel pellets tend to gain electrons and become negatively charged. The result is a massive separation of charge. The top of the cloud becomes a dome of positive energy. The bottom of the cloud, the flat base, becomes a pool of negative energy. The atmosphere is now a giant battery. Air is normally an insulator. It does not want to conduct electricity. But as the negative charge at the bottom of the cloud builds, it begins to repel the electrons on the ground below. The electrons in the grass, trees, and buildings are pushed deeper into the earth, leaving the surface positively charged. The voltage difference between the cloud and the ground can reach 100 million volts. Eventually, the air breaks. It begins with the stepped leader. This is a channel of negative charge that shoots down from the cloud. It is invisible to the human eye. It moves in jerky steps, roughly 50 yards at a time, pausing for a fraction of a microsecond between each jump. It is searching for a path of least resistance. As this invisible tentacle gets close to the ground, within a few hundred feet, the positive charge on the earth reaches up to meet it. Tall objects, trees, lightning rods, people send up streamers, faint purple fingers of positive charge. When the stepped leader connects with a streamer, the circuit is closed. Whoosh! A massive surge of electrons dumps from the cloud to the ground. This is the return stroke. This is the bright flash you see. Counterintuitively, The visible part of the lightning actually travels up from the ground to the cloud, retracing the path of the leader. It happens at 1/3 the speed of light. The energy involved is staggering. A single bolt carries about 30,000 amps of current. It heats the narrow channel of air, about the width of a pencil, to 50,000 degrees Fahrenheit. This is 5 times hotter than the surface of the sun. This sudden, extreme heating creates thunder. The air inside the channel is heated so fast that it doesn't have time to expand gently. It explodes. The pressure rises to 10, maybe 100 atmospheres in a microsecond. This creates a supersonic shock wave that rips through the surrounding air. Close to the bolt, the shock wave is moving faster than the speed of sound. This is the sharp crack or snap you hear when lightning strikes nearby. As the wave travels outward, it slows down and stretches out, becoming the low, rolling rumble of distant thunder. Because light travels almost instantly, 186,000 miles per second, and sound travels slowly about 1 mile every 5 seconds, you can calculate the distance of the storm. Count the seconds between the flash and the bang, then divide by 5. That is your distance in miles. Most lightning, about 80%, never hits the ground. It stays inside the cloud, jumping between the positive and negative regions. This is intra-cloud lightning, sheet lightning. It lights up the sky like a flickering light bulb but produces no thunder that you can hear on the ground. But occasionally, the polarity flips. In rare positive giants, the bolt originates from the top of the anvil, the positive region, and strikes the ground miles away from the storm in the clear blue air. These bolts from the blue are far more powerful than normal negative lightning. They can carry 10 times the current and last 10 times longer. They are the most dangerous form of lightning, capable of striking people who think the storm has already passed. If a thunderstorm is a heat engine, a tornado is its exhaust pipe gone wrong. It is nature's most violent wind, capable of stripping asphalt from roads and tossing freight trains like toys. A tornado is born from a supercell. We mentioned earlier that wind shear, a change in wind speed or direction with height, can tilt a storm. But shear does something else too. It creates rotation. Imagine a paddle wheel placed in a river. The water at the surface moves faster than the water at the bottom. This difference in speed makes the paddle wheel spin. The same thing happens in the atmosphere. If the wind at 5,000 feet is blowing strongly from the west, but the wind at the ground is calm or blowing from the south, you get a horizontal tube of invisible air rolling along the ground like a rolling pin. This horizontal roll is harmless until the updraft catches it. As the warm, buoyant air of the thunderstorm rushes upward, it tilts this rolling tube of air into the vertical. Now, instead of rolling along the ground, it is spinning like a top. This creates a mesocyclone. A mesocyclone is a rotating updraft, typically 2 to 6 miles wide. It is the heart of a supercell. If you watch a time-lapse video of a supercell, you can actually see the entire storm rotating. The wall cloud, a lowering of the cloud base, often rotates with it, but a mesocyclone is not a tornado. It is too wide and rotates too slowly. To get a tornado, you need to concentrate that spin. This happens through the conservation of angular momentum. Think of a figure skater. When she spins with her arms out, she rotates slowly. When she pulls her arms in tight to her body, she spins incredibly fast. The same physics applies to the storm. As the updraft stretches the mesocyclone vertically, it forces the rotating column of air to become narrower. As the radius shrinks, the speed must increase to conserve momentum. The wide, slow rotation of the mesocyclone tightens into a narrow, violent vortex. This vortex begins high in the cloud. We see it as a funnel cloud. It is a cone of condensed water vapor spinning downward. It becomes a tornado only when the circulation reaches the ground. Crucially, the visible funnel doesn't have to touch the ground. If you see debris swirling on the surface underneath a funnel, it is already a tornado. The pressure inside the core of a tornado is incredibly low, often 10% lower than the surrounding air. This pressure drop is so extreme and sudden that it acts like a vacuum cleaner. It sucks air in from all directions. This inflowing air expands and cools rapidly, adiabatic cooling, which condenses water vapor. This is why the tornado is visible. You are seeing the cloud forming instantly in the low pressure of the vortex. The dark color usually comes from the dust and debris it has already picked up. Meteorologists rate tornadoes on the enhanced Fujita EF scale. This scale is not based on wind speed measurements, because weather instruments are usually destroyed. It is based on damage. EF 0, 65 to 85 miles per hour. Minor damage, shingles blown off roofs, branches broken. EF 1, 86 to 110 miles per hour. Moderate damage, mobile homes pushed off foundations, cars blown off roads. EF 2, 111 to 135 miles per hour. Significant damage. Roofs torn off frame houses, large trees snapped. EF 3, 136 to 165 miles per hour. Severe damage. Entire stories of well-constructed houses destroyed, heavy cars lifted and thrown. EF 4, 166 to 200 miles per hour. Devastating damage. Well-constructed houses leveled completely, cars thrown hundreds of yards. E5 over 200 miles per hour. Incredible damage. Strong frame houses leveled and swept away, leaving bare foundations. Automobile-sized missiles fly through the air over 100 yards. High-rise buildings have significant structural deformation. An EF5 tornado is a rare beast, less than 0.1% of all tornadoes. In these monsters, the wind speed can exceed 300 miles per hour. At these speeds, straw can be driven into telephone poles and wood can pierce concrete. The wind is so powerful it scours the earth, removing the topsoil and leaving nothing but bare rock behind. The life of a tornado ends when the rear flank downdraft, RFD, wraps completely around the cyclone. This is a curtain of cold, sinking air that spirals around the funnel. It chokes off the supply of warm, moist inflow. The tornado ropes out, thins into a snake-like tube and dissipates. If a tornado is a chaotic, short-lived spasm of violence, a hurricane is a massive, organized engine of destruction. It is the largest storm system on Earth. A hurricane, or typhoon, or cyclone, they are the same thing, is a heat engine. It is a machine that extracts heat energy from the warm ocean surface and converts it into mechanical energy, wind. To build one, you need fuel. That fuel is warm water. Specifically, the ocean must be at least 80 degrees Fahrenheit, 27 degrees Celsius, to a depth of 150 feet. This deep reservoir of heat is crucial. As the storm churns the water, it mixes cold water from below. If the warm layer is too shallow, the storm kills its own fuel supply. The process begins with a cluster of thunderstorms moving off the coast of Africa, a tropical wave. As air rises in these storms, it lowers the pressure at the surface. Air rushes in to fill the gap. But because of the Coriolis effect, this rushing air starts to spin. Crucially, this spin cannot happen at the equator. The Coriolis force is zero at the equator. A hurricane needs to be at least 5 degrees latitude, about 300 miles away from the equator, to get enough twist. This is why no hurricane has ever crossed the equator. As the air spirals inward, it picks up massive amounts of heat and moisture from the ocean. This is the evaporation-condensation feedback. 1. Evaporation. The wind speeds up evaporation. The faster the wind blows over the water, the more water vapor it picks up. 2. Condensation. The moist air spirals inward and shoots upward in the eye wall. It condenses, releasing huge amounts of latent heat. 3. Pressure drop. This heat warms the core of the storm, making the air lighter. The pressure drops even further. 4. Wind increase. The lower pressure sucks in air even faster. This increases the wind speed, which increases evaporation, and the cycle explodes. At the center of this spinning monster is the eye. The eye is a paradox. It is the calmest part of the storm. Inside the eye, which can be 20 to 40 miles wide, the winds are light and the sky is often clear blue. This happens because of conservation of angular momentum. As the air spirals in faster and faster, centrifugal force throws it outward. It literally cannot reach the center. Instead, it hits a wall, the eye wall, and shoots straight up. The eye wall is the ring of violence surrounding the calm eye. This is where the strongest winds, up to 185 miles per hour, and heaviest rains are found. It is a vertical stadium of thunderstorms reaching 10 miles high. At the top of the storm, the air spreads out. This outflow acts like a chimney, venting the exhaust heat into the upper atmosphere. If this chimney gets clogged by wind shear, the storm dies. A hurricane is essentially a massive, breathing organism. It inhales warm, moist air at the bottom and exhales cold, dry air at the top. The destruction comes from 3 sources. 1. Wind. The sustained force can tear roofs off houses and turn debris into missiles. 2. Rain. A slow-moving hurricane can dump 50 inches of rain in a few days, like Hurricane Harvey, causing catastrophic inland flooding. 3. Storm surge. This is the most deadly part. The low pressure of the eye sucks the ocean surface upward like a straw. Combined with the relentless wind pushing the water, this creates a dome of water 20 to 30 feet high. When this dome hits the coast, it acts like a tsunami, sweeping everything away. Hurricanes have a natural lifespan. They die the moment they move over land or cold water. They are cut off from their fuel source, the warm ocean. Friction with the ground tears the circulation apart. The eye collapses, the winds fade, and the monster dissolves back into a chaotic mess of rain showers. The atmosphere is not just a fluid, it is a lens. It is a chaotic, shifting prism that bends, scatters, and breaks light into its component wavelengths. Every time you see a blue sky, a red sunset, or a rainbow, you are witnessing a collision between a photon from the sun and a molecule of air or water. The most fundamental optical effect is the color of the sky itself. Sunlight appears white to our eyes, but it is actually a mixture of all colors, the visible spectrum. When this white light hits the gases in our atmosphere, mostly nitrogen and oxygen, it scatters. This is Rayleigh scattering. Shorter wavelengths, blue and violet, are scattered much more strongly than longer wavelengths, red and orange. The blue light is bounced around in every direction by the gas molecules until it seems to be coming from everywhere at once. This is why the sky is blue. We don't see the violet because our eyes are less sensitive to it, and because the sun emits less violet light to begin with. At sunset, the light has to travel through a much thicker slice of atmosphere to reach your eye. The blue light is scattered away completely before it gets to you. Only the longer, resilient red and orange wavelengths can penetrate that distance. The sky turns to fire because the blue has been filtered out, but the most spectacular displays happen when light hits water. The rainbow. A rainbow is a personal event. No two people see the exact same rainbow because it is an optical illusion created by your specific angle relative to the sun and the rain. To see one, the sun must be behind you and the rain must be in front of you. When a beam of sunlight enters a spherical raindrop, it slows down and bends. This is refraction. The light separates into its colors, dispersion just like in a glass prism. The separated light then hits the back of the raindrop and reflects off the inner surface like a mirror. Finally, it exits the front of the drop and refracts again, spreading the colors even further apart. The geometry is precise. Red light exits the drop at an angle of 42 degrees relative to the incoming sunlight. Violet light exits at 40 degrees. Because of this fixed angle, you see red light coming from droplets higher in the sky and violet light from droplets lower in the sky. The result is a perfect arc, or a full circle if you are in an airplane centered on the anti-solar point, the shadow of your head. Sometimes you see a double rainbow. This happens when the light reflects twice off the back of the raindrop before exiting. This second reflection flips the order of the colors. In the primary bow, red is on the outside. In the secondary fainter bow, red is on the inside. The dark band of sky between the two bows is called Alexander's band, named after Alexander of Aphrodisias, who first described it in 200 AD. It is dark because no light is scattered into that specific angular zone. Halos and sundogs. If rainbows are the children of rain, halos are the children of ice. When high, thin cirrus clouds cover the sky, they are filled with millions of hexagonal ice crystals. These crystals act like tiny, six-sided prisms. If the crystals are randomly oriented, the light refracting through them creates a perfect ring of light around the sun or moon. This is the 22-degree halo. It is always exactly 22 degrees in radius because of the specific refractive index of ice. Folklore says a ring around the moon means rain is coming soon, and it is often true, as cirrus clouds precede a warm front. If the ice crystals are flat plates falling horizontally like dinner plates, the refraction concentrates the light into two bright spots on either side of the sun. These are parhelia, or sundogs. They often look like mini-suns or brilliant rainbow patches flanking the true sun. Mirages. Finally, the atmosphere can act like a funhouse mirror. This is a mirage. A mirage is not a hallucination. It is a real image of the sky or ground displaced by bent light. It is caused by temperature differences in the air density. The most common type is the inferior mirage, the puddle on the road. On a hot day, the asphalt is scorching. The layer of air touching the road is much hotter and less dense than the cooler air a few feet up. Light travels faster through hot, thin air. Light rays coming from the blue sky approach the road, hit the hot air, and speed up so much that they bend refract upward into your eye. You are literally seeing the sky on the ground. Your brain interprets this blue patch on the road as water. It is an image of the horizon projected onto the asphalt. The opposite is the superior mirage. This happens in polar regions where the ground is freezing and the air above is warmer, a temperature inversion. Light from objects beyond the horizon bends downward toward the viewer. This can make a ship or an iceberg appear to float in the sky, upside down. This phenomenon, Fata Morgana, is likely the source of the Flying Dutchman legend, ghost ships sailing through the clouds. We have now seen the immense power of the atmosphere, the heat engine, the water battery, the violence of tornadoes, and the beauty of rainbows. It seems like a perfect machine, governed by the unbreakable laws of physics. If we know the laws, fluid dynamics, thermodynamics, why can't we predict the weather perfectly? Why does the forecast say sunny and you get rained on? The answer lies in a branch of mathematics called chaos theory. In the 1960s, a meteorologist named Edward Lorenz was running a computer simulation of the weather. He wanted to redo a forecast, so he typed in the numbers from a previous run. But instead of typing the full 6-decimal precision 0.506127, he rounded it off to 3 decimals, 0.506. He assumed the difference, less than 1 part in 1,000, was too small to matter. He went to get a coffee. When he came back, the computer had produced a completely different weather pattern. This was the discovery of the butterfly effect. The idea is poetic but mathematically precise. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The atmosphere is a non-linear system. This means that small changes in the initial conditions, like a slight shift in wind direction or a temperature difference of 0.1 degrees, don't just fade away. They amplify. They grow exponentially over time. Because we cannot measure every single molecule of air on Earth, we cannot know the exact temperature, pressure, and wind speed at every inch of the atmosphere. Our starting picture is always slightly imperfect. We have gaps in our data over the oceans, the poles, and the upper atmosphere. These tiny errors in our initial snapshot grow. Day 1, the error is negligible. The forecast is 95% accurate. Day 3, the error has doubled. The forecast is roughly right, but the timing of the rain might be off by a few hours. Day 7, the error has multiplied by a factor of 10. The model says storm, but reality might be sunny. Day 10, the error has overwhelmed the signal. The forecast is no better than guessing based on historical averages, climatology. This creates a prediction horizon. No matter how powerful our computers become, no matter how many satellites we launch, we will likely never be able to predict the specific weather more than 2 weeks in advance. The chaos of the fluid is a fundamental limit of the universe, not a failure of technology. To fight this chaos, modern meteorologists use ensemble forecasting. Instead of running one computer model, they run the same model 50 times. In each run, they slightly tweak the starting conditions, making the air a tiny bit warmer here, or the wind a tiny bit faster there. If all 50 models show a hurricane hitting Florida, the confidence is high. The atmosphere is in a stable state. If 20 models show a hurricane, 10 show it going out to sea, and 20 show nothing at all, the confidence is low. The atmosphere is in a chaotic state. This is why you see cone of uncertainty maps, or 30% chance of rain. It is a direct measure of the chaos in the system. Yet, Despite this limit, numerical weather prediction is one of the greatest scientific achievements of the 20th century. We have turned the sky into a math problem. We solve billions of differential equations every second to tell you if you need an umbrella tomorrow. We cannot control the weather. We cannot perfectly predict it. But by understanding the physics of the ocean of air, we have learned to live within its turbulent, beautiful, and deadly flow.